Okay, kids, I'm probably not going to be there tomorrow. My wife got COVID and we got the results late Friday night. So I have to take a test tomorrow. Couldn't find a place today, even though my at-home test really came out negative. I just did it because I got home from Big Bear. All right, there are a few things that you need to do tomorrow. Number one, you need to finish your booklets. Number two, you didn't turn in your enzyme web quest again. So you guys need to do this, and seriously. Now, there's two different options. I'm going to show you a video on tonicity as well. I want to watch you and teach you at least something. If perhaps, and I think I'm not going to test positive, I'm hoping not, then I'll be back at school on Tuesday. Now, if I do test positive, that means I have to take 5 days off, and look forward to more of these videos. All right, let's get into the next thing, tonicity.
Should you drink seawater or not?
No.
Stick with us. We're going to find out and also review hypertonic, hypotonic, and isotonic solutions along the way.
With comments from Miss
Cells have a
Morgan.
very finite range of conditions in which they can survive. If it's too hot, too cold, too watery, too salty, too acidic, or too basic, they can't function properly. We're going to explore what happens when you place a cell in a solution that is much more salty, hypertonic, much more watery, hypotonic, or has an equal salt concentration, isotonic.
Okay, so I'm going to stop things really quick. I always use hyper and say somebody's hyper is really burning a lot of energy. So this thing is going to shrivel. Okay, so that means that these water molecules are going to move from the inside to the outside of the cell. What's going to happen? It's going to shrivel up. Now, hypotonic is just the opposite. The water, do you see the water cells? They're mostly on the outside, and there's very few on the inside. So they're going to go into it, and they're drawn to the salt, right? Okay, they're going to be drawn to the salt, okay, and it's going to swell up and maybe burst. Now, what we want is a balanced solution like isotonic, where we have basically equal numbers of molecules inside and out. And if you count these, it'll probably be close to the same. All right, let's see what the rest of this video says.
Remember that cell membranes are selectively permeable. They allow certain particles to pass through, but not others. Usually, larger molecules can't fit through the membrane without special
This is
channels.
called an
The cell
aquaporin.
membrane is fitted with special protein channels called aquaporins, which allow water molecules to pass through without expending energy. However, the ease with which the water molecules can cross is going to depend on something called the concentration. Concentration is a measure of how much solute there is per volume of solvent. In other words, whether the liquid is more salty or more watery. We'd usually expect that the molecules would follow a process called diffusion. They would flow from areas of higher to lower concentration.
Very important.
Eventually,
Diffusion.
they will reach equilibrium, where there will be an equal concentration on both sides of the membrane.
And osmosis is when water molecules specifically flow from high concentration to low concentration.
However, in the case of a liquid like salt water, the salt molecules are much, much too big to fit through the membrane. So the only particle that can move is water. Let's look a little more closely.
Cell
Water
membrane
molecules
we're
are
talking
highly
about.
attracted to salt molecules. They cluster around salt and really, really don't want to move. The positive parts of the water molecule stick to the negative parts of the sodium chloride, and vice versa. The interactions between oxygen and sodium and between hydrogen and chlorine are called ion-dipole interactions,
You don't have to worry
which you
about
might
that
remember
till
from
next year.
chemistry. Water molecules that are not stuck to a molecule of salt are far more likely to relocate. Today we're going to immerse a cell in 3 kinds of liquids: a very solute-rich liquid, a very watery liquid, and a liquid that's in between. Then we'll see what happens to the water molecules. In this first scenario, the liquid surrounding the cell has many molecules of solute in it. This liquid is hypertonic compared to the cell. It has a much higher concentration of solute particles and a much lower concentration of water. Unfortunately, the solute molecules can't pass through the membrane to reach equilibrium, but water molecules can. The molecules of water on the outside of the cell are going to be obstructed from passing through by the many molecules of solvent. However, the molecules on the inside have much less solvent getting in the way. Water will begin rushing out of the cell. Some water will come in, but the net movement, the overall movement, of the water molecules will be outwards and the cell will shrink. We call this cell contraction plasmolysis. This is also how pickles are made. Now let's immerse a cell in a much less concentrated solution, a
Hypotonic.
hypotonic
Everything's going
solution.
to go
Compared
inside
to the cell, it's
and they'll
much
burst.
less salty. Some water molecules will exit the cell, but even more will rush in because they aren't obstructed by solute particles. The cell grows in size and it may even undergo cytolysis and burst. Placing a cell in an isotonic solution, where the concentrations inside and outside are equal, is much more pleasant. Equal amounts of water molecules continue to pass in and out of the cell. The system is in dynamic equilibrium. Particles are continuing to move, but the net movement is zero. The cell neither grows nor shrinks and is much more likely to survive. Now let's return to our seawater question. Seawater is incredibly salty, much more salty than our body's cells. Since it's such a hypertonic solution, if you immersed your cells in it, they would shrivel up and die. The real danger, however, lies in how your kidneys would react to the seawater. Your kidneys would attempt to remove the toxic levels of salt by using water pulled from your cells. Your body would actually use more water in removing the salt than was originally contained in the seawater itself. In summary, drinking seawater is a lousy idea even in extreme circumstances. You're better off drinking your own pee. So there we have it. Hypertonic, hypotonic, and isotonic solutions, as well as a couple of practical examples. If you found this video useful,
Okay, please refrain from drinking your pee or going onto islands.